All right, let's talk about taming the absolute chaos of concurrency. I mean, if you've ever built a system that has to do more than one thing at a time, you know exactly how fast things can get, well, complicated. Today, we're going to break down the proven, battle-tested strategies to make your app safe, efficient, and ready to scale. Let's dive in. So first, let's set the stage. This isn't just some abstract theory you learn in school. For developers building pretty much anything today, concurrency isn't just a nice to have, it's a hard requirement. And when it goes wrong, it's not just a bug, it's a full-blown crisis. You know the feeling, right? Your application runs perfectly on your laptop, but then you push it to production, the users pile in, and suddenly it starts to slow down, it freezes, or it just completely crashes. What is going on? Well, 9 times out of 10, the root cause is how you're managing, or more likely, failing to manage, all those tasks happening at once. And look, these aren't just random, unrelated bugs. They're the classic telltale symptoms of concurrency gone wrong. You've got race conditions where threads trip over each other and corrupt your data. You've got deadlocks where your whole system just freezes solid, waiting for something that's never going to happen. Then there's thread explosion, where you just burn through all your system resources. And the one we've all felt, the dreaded unresponsive UI. All of these point back to the same fundamental problem. But here's the good news. These are solved problems. Seriously, we do not have to reinvent the wheel every single time. There's a proven, battle-tested toolkit designed specifically for these challenges, and it's called Multithreading Design Patterns. So what are these things exactly? The best way to think about them is like architectural blueprints for your code. They are reusable, well-understood solutions to these common concurrency problems. So instead of just guessing and hoping for the best, you can apply a pattern that is known to work safely and efficiently, especially when you need to scale up. And here's a look at that core toolkit. Now, there are a bunch of patterns out there, but for today, we're going to zero in on 3 of the absolute most fundamental ones, the ones you're going to see and use all the time: the thread pool, the producer-consumer pattern, and the future/promise pattern. All right, let's roll up our sleeves and get into the details. For each of these patterns, we're going to look at the exact problem it solves, how it actually works under the hood, and most importantly, why it's so critical for building solid, robust systems. First up, the thread pool. This one is absolutely fundamental. The problem it solves sounds simple, but it is a silent killer for applications. If you spin up a brand new thread for every single request that comes in, your system will eventually run out of resources and die. It's just way too expensive. The solution, though, is so elegant. Instead of constantly creating and destroying threads, we just create a fixed number of them up front and reuse them over and over. Okay, so let's trace the flow. Picture this. All your incoming requests get dropped into a task queue. Meanwhile, you have this pool of worker threads just waiting. An available thread grabs the next task from the queue, does the work, and then, and this is the absolute key, it doesn't die. It just goes right back into the pool, ready for the next job. This completely avoids that super expensive cycle of creating and destroying threads. So what's the big takeaway here? Using a thread pool prevents that dreaded thread explosion, which gives you a massive boost in performance and stability. It gives you, the developer, direct control over your resource usage. You're basically putting a hard ceiling on how many things can happen at once, which is a game changer for reliability. Next up, the producer-consumer pattern. Imagine one part of your system, the producer, is just churning out work way faster than another part, the consumer, can actually handle it. This mismatch is a classic recipe for disaster. It causes backlogs, memory issues, and crashes. The solution is to put a buffer right in between them. So here's how it works. You have producers on one side, adding items to a shared blocking queue. Then you have consumers on the other side, pulling items out of that same queue. The queue itself acts like a shock absorber. If the queue gets full, it automatically tells the producers to just chill out for a second, and if it's empty, it tells the consumers to wait. It just naturally balances the workload between the two. And why does this matter so much? Well, it lets your system handle sudden bursts in traffic without breaking a sweat. But maybe even more importantly, it decouples the producer from the consumer. They don't need to know anything about each other. They only know about the queue. This makes your whole system way more modular, flexible, and resilient. Okay, our last deep dive is the future, or promise pattern. We have all been there. You click a button in an app, and the entire thing just freezes because it's stuck waiting for some slow network call or database query. The solution here is to simply not wait. When you kick off that long-running task, you immediately get back a special object, a future. And that's basically just a promise, a placeholder that says, hey, I'll have a result for you eventually. And the impact is huge. Your main thread is now totally free to keep the UI snappy and responsive. All that heavy lifting is happening on some other thread in the background. This lets your system make full use of modern multi-core processors. I mean, this is the absolute foundation of modern async programming, and it's what makes apps feel fast and fluid instead of slow and clunky. Okay, so we've been deep in the weeds on 3 specific patterns. Now let's kind of zoom out and look at the big picture. Because using these patterns isn't just about fixing little bugs, it's about fundamentally architecting your systems for scale and stability right from the very beginning.
You can see the direct link right here. A thread pool gives you control over thread growth. Producer consumer is your go-to for handling load spikes. You can even see some others, like fork joint, which is all about breaking a massive task into tiny pieces to max out all your CPU cores. Each pattern is a specialized tool for a very specific scaling challenge.
And remember, it's not just about going faster. It's about not falling over. These patterns are critical for reliability. By combining things like a thread pool and a queue, you create this natural back pressure. It's a way for your system to gracefully say, whoa, I'm at capacity, let's slow down a bit. This is what prevents overload, and it leads to far fewer crashes and much more predictable performance when things get stressful. Okay, so we've got all this great theory, but what do you actually do with it? How do you take this knowledge and apply it to your own code? Let's talk about that. But first, and this is super important, no design pattern is a magic bullet. Not a single one. Every single pattern comes with trade-offs, and being a great engineer is all about understanding which trade-offs you're willing to make in a given situation. Let's take the thread pool. The pro is amazing resource control and stability. But the con? Well, during a huge traffic spike, some of those new tasks might have to wait in the queue for a little bit. You're making a conscious choice. You're trading immediate execution for long-term system stability. What about producer-consumer? The pro is this beautiful decoupling of your system's components, but the trade-off is that now you have a new puzzle to solve. How big should that buffer queue be? If it's too small, your producers are going to get blocked all the time. But if it's too big, you could end up using a ton of memory. It's a balancing act. And finally, with futures and promises, you get that incredible responsiveness. But the complexity doesn't disappear, it just moves. Now, you have to think really carefully about what happens when that background operation fails. Handling errors in an async world is incredibly powerful, but it definitely requires a different way of thinking than good old-fashioned sequential code. And that brings us to the end. We've seen the crisis, we've opened up the toolkit, and we've weighed the trade-offs. So now that you have these patterns in your mind, think about your own systems. Think about your own code. Where's that hidden bottleneck? Where's that one spot that always feels a little shaky under load? The real question is, which part will you refactor first? Thanks for joining me.